worry about it because they're here. How about this? It's the outcry.
Thank you for coming this evening.
It's always
It's not pleasant out there, but I think we're all accustomed to this kind of weather. It's not Buffalo, but I think we can handle it.
Jack, I don't know if your microphone.
Can you hear it? Oh my goodness. I thought I was a big mouth.
Now you are.
No, I am. You know what I'd like to do first is, for those people who are from Fenner, would you raise your hand? And from Cazenovia? Oh, good. About time. And from Pompey or other communities?
Nelson.
Well, that's a good show. From Cass College? Hey.
Hey.
From Cornell.
How about Morrisville?
Well, I took around some posters, and I found something out that I didn't know. I kind of knew it, but I wasn't sure. When I asked permission to put a poster up, people kept saying, in general, all of them said the same thing. Oh, good. It's about time that we've had a chance to listen to what's happening. All of us are bombarded every day by information. And sometimes we kind of let it slip over our shoulder and say, oh yeah, right. But tonight we have someone here who can give you answers. Now I know you know what peer-reviewed science is. That's important to know. That's when you find out what not one scientist is saying, but other scientists who agree with that. And tonight we have that. And we're going to listen to what he has to say, and then we're going to have a chance to ask him questions, so that we leave here educated and not just guessing what this is all about. Because what it's about is important to each of us. Now, Cazenovia is different than Fenner. Fenner is a wild, wonderful landscape of central New York. It's magnificent when you drive around it. Especially this time of year. It's my favorite time of year to drive. Cazenovia is different. It has wild areas, but it has a unique community. When many of us travel, people will ask us where we're from. Invariably, it happens all the time. When you say Cazenovia, actually we usually say Syracuse, but I live in Cazenovia. People will say, I know that place. That has that wonderful restaurant, hotel on a corner. What's the name of it? And we all say it's the Link Lane House. So people know this place for a good reason. They know it because it's part of our history. It's a place that belongs to the heritage of the community. And that's what we want to keep. Those who live in Fenner and those that live in Cazenovia or Pompey, we want to remember what we have. It's a place that we're at for a while, and we'll pass on, and someone will follow us, and hopefully it'll stay the same. And tonight we'll find out why that may not be possible. And that's important for us to know. We need to be educated. I'm going to give you some statistics, and then I'm going to pass this on. I'm going to give you statistics because it's important for you to know. DEC did a study, very extensive study, I read every single page of it, and my God, was it boring. But what struck me was one portion of it that talked about truck traffic, convoys of trucks. Let me give you statistics that DEC has. This is not something that comes out of the air. This is what they studied from going down to Pennsylvania and West Virginia and studying those areas. They found that when you're fracking, the actual construction of and the drilling of fracturing the shale rock, you have 900 to 1,350 truckloads a day going to and coming from that site for a well. That's a lot. If you take 900 of those, the lowest number, that's one truck every 1.6 minutes. So if you live on the West Lake Road or East Lake Road or Shenango Street or Fenner or Farnham or Lake Lane, you could possibly have in front of your house 24 hours a day, 7 days a week, 1.6 trucks per minute driving by. And right now we have, what? A milk truck. One in the morning, one in the afternoon. 18 wheels, big truck. Makes a lot of noise. Not much diesel fuel, but 1.6 per minute. A lot of noise and a lot of change in our lives. Think about Bachville weekend. You can't get through Cazenovia on Bachville weekend. Hundreds of cars. Well, that could be every single day with trucking. And things can be done about that if you decide to do something. 1.6 trucks per minute. I'm going to turn this over to Phil Rose in a minute. But after our speaker finishes, we're going to hand out to you a request for your opinion on whether or not we should have fracking or not in our area. It makes no sense to do it now, but it does make sense after you hear what's going to happen tonight. Bill Rose is a resident of Fenner. He's a Boston College graduate, got a master's at Syracuse University, and formed a group to study and determine what is best for Fenner as far as fracking is concerned. And what he found was, after meeting with these people, 75% of the registered voters in Fenner agreed to ban fracking. That's a lot. That's an awful lot of people. Has that happened in Cazenovia? We don't know what's happened in Cazenovia. It's been kind of kept to our chest. And what we need to do is understand better what it means to us. 1.6 trucks per minute by your house, in your village, with that noise. As somebody once said, I came to Cazenovia to retire because I came back home. I didn't come here for 1.6 trucks per minute. Phil Rose.
Thank you, Jack. I'll give a shout out for Fenner. People have no idea where Fenner is when you say, oh, I come from Fenner. But then you say, what? They have the what?
Windmills.
Windmills. Oh, that's Fenner. Oh, yeah. And there we go. Didn't one of those fall down? I always remember that part, too. So welcome, everybody. Glad you're here. This is going to be an important evening for all of us, no matter where you stand on this issue. There's a lot of feelings around this issue, a lot of powerful feelings, and rightfully so. People have a lot of charge one way or the other on this, and it's good. It's good to acknowledge how powerful we feel. But ultimately, what we need to do is come to some reasoned positions and policies around this issue and make the best choice that makes the best sense, not how powerful we feel about any aspect of this. So Dr. Ingraffia here is a man whom I've listened to before. I went down to Cornell and listened to him debate representatives from the gas industry and on a panel. And I just was struck by his calm, reasoned, thoughtful approach to this entire issue, because it is so volatile and people get a little carried away with the rhetoric, and I'm subject to that myself occasionally. But Tony's been doing this for a while. He's grown in his own wisdom and his own understanding of this. He's been challenged at every turn on what he's come up with, and he's been listened to, and he's one of the key spokespersons. So without further ado, I want to introduce Tony Ingraffia, who is the Dwight C. Baum Professor of Engineering at Cornell University. Tony.
Good evening, everyone. First test. Can you hear me in the back?
Yes.
No? Yes?
Use
the mic.
Yep.
Okay.
Yes.
Good. So, good evening, everyone. And I want to thank you all for inviting me to be with you and interact with you tonight. Cazenovia is a beautiful city. It's my first time here. I can't believe it. I've been to literally dozens of small communities in upstate New York and northern Pennsylvania over the last 6 years doing what I'm doing tonight, which is informal education with the public. It's a real privilege to do that. I realize it's a sacrifice of time and effort on your part to be here. So I promise you I will do the very best I can to bring you the latest information on the science, the engineering, and the technology behind what you call fracking, but what I don't call fracking. I call it development of shale gas and oil. And for reasons you'll see during the course of the next 3 hours or so. I've been told that every community in upstate New York has a unique attribute, and I've been told by many people outside of Cazenovia and Fenner and surrounding communities that this area of New York State has the most sophisticated sense of humor of any place in New York. You will be tested. Even though what we're talking about isn't very funny, I'll try to make sure that I communicate in a way that everybody gets it. So let me begin by saying that everything I'm going to present to you tonight in engineering, science, technology is fact-based, it's objective, it's the result of scientific investigations, peer-reviewed publications, and/or official government and/or official oil and gas industry publications. I can also assure you that my interpretation, my personal interpretation of what I'm going to present to you tonight is not objective. It is extremely subjective. So I need to tell you a little bit about why I have not only the privilege to be with you tonight, but the right to be talking to you about these things. I will not be blowing smoke. My PhD is in rock fracture mechanics. How many other PhDs in rock fracture mechanics are there in the room? I suspect that there might be 2 other people with PhDs in rock fracture mechanics in the state of New York. So what? That tells you that from my early age of 1870s, I was studying how to get things out of rock, because why else would you break rock? Well, there are some other reasons, tombstones, stuff like that. But you break rock to get stuff out of it. Oil, gas, coal, heat, water. And I came to Cornell in 1977. For the next roughly 25 years, I worked with the oil and gas industry. as a consultant, a paid consultant, and as a researcher. The oil and gas industry, I can name names if you want to hear them, paid Cornell University millions of dollars to have me and my graduate students perform research and development for the oil and gas industry. So I worked with a large number of people in the oil and gas industry, scientists and engineers. I published with them. I did experiments out in the field. I did experiments in the laboratory. We developed computer software together. And so I understand the industry. I worked on hydraulic fracturing for a long time. I was in the very early stages of how to get gas and oil out of shale in the early 1980s. I was working at the Lawrence Livermore National Laboratory on a sabbatic, and your tax dollars funneled through the Department of Energy were focused on a question that was just beginning to be asked then. Do we have any oil or gas in shale? And if so, how the hell do you get it out? Because nobody had tried. Up until that time, until actually the mid-1990s, nobody, with a few exceptions around the world, was trying to get oil or gas out of shale. It was judged to be the single most difficult rock to get anything out of. It was left to the end. All the easy stuff came first, and then the less easy stuff, and then the less easy stuff. I mean, they were drilling wells in 2,000 feet of water and 30,000 feet of rock in the Gulf of Mexico before they started trying to get oil or gas out of shale. So that tells you what the industry thought about getting oil or gas out of shale. And so I was there at the very beginning, and so the point I'm trying to make here is I know what I'm talking about. And what I'm going to talk about tonight is the science and the technology and the engineering behind getting gas and oil out of shale. And yeah, I know it's kind of boring. I mean, depressing nowadays that a lot of bad things happening in the world, and I don't want to depress you tonight, but I'm telling you my opinions about what I'm about to say are depressing. Having worked with the industry all that time, I now am absolutely certain they're doing the wrong thing for us. So I want to make that clear right up front. All right, an outline. I've chosen 3 topics from the many possible things that we could talk about tonight and how to get oil or gas out of shale. I picked 3 topics that are strongly suggested by the advertisements running on TV nowadays. Fracking is safe. It's been done for 60 years. What's the worry about it? I mean, there's been fracking in New York State since the early 1900s. There's fracking in New York State today. New York State does not have a ban on fracking. New York State has a current moratorium on shale gas development, but fracking's been around a long time. Why worry about it? I'll give you my opinion about why we should. Second thing you hear about is that our wells are encased in 4 layers of steel and cement and they never leak. So if somebody's water well is getting contaminated, we did not do it. Your water was always contaminated, you just didn't know it. And the third one is methane, natural gas. Here's the chemistry lesson for tonight. Natural gas is methane, CH4. 1 carbon, 4 hydrogens. The simplest of all hydrocarbons. Methane, natural gas, is a clean fossil fuel. It's the bridge to the future. Well, maybe not exactly clean, but it's cleaner. And it is a bridge. So these are 3 statements you hear from the President of the United States, you hear them from our Department of Energy, from the EPA, from advertisements, you hear them from lots of places, as you just heard from the introduction. You get bombarded with this. So my job tonight is to try to convince you otherwise, that these are in fact non-factual statements, not supported by the science and the engineering. I'll do my best to try to do that, and during Q&A you can challenge it. So we'll take these lists one at a time, and I'm going to pick the first one for a specific reason. It's also going to give us an opportunity to do shale gas development 101. How do you go about drilling, casing, cementing, perforating, fracking, flowback, compression, dehumidification, processing, distribution, transmission, distribution, burning. The whole life cycle. How does it all work? You're going to get that in 10 minutes. And then there's an exam. All right, so in contrast to this, fracking has been around for 60 years. There are no new concerns. I'm going to try to explain to you why fracking in shale is different. It is relatively new, and it involves technologies and engineering that weren't ever used until the last 10 or 15 years, and have never been used in New York State. And I'm going to try to show you that while using those technologies, we have intensified air, water, light, sound, and dust pollution, and lots of emissions, and lots of opportunity for loss of drinking water. So, how does it work? This is shale gas development current, state of the art. This is how it has to work for the companies to make money. Ready? This is a cartoon originally put together by one of the largest gas producers in the country, Chesapeake. And I doctored it up with some additional information to make it more reasonable. So let me tell you what's going on, because this is what you need to know, because this is what would be coming to town. Here's the surface. Beautiful countryside around Benner, right? Development begins with the construction of a pad. A pad is an area where the drilling occurs. I'll show you pictures of actual pads. On each pad, there are a number of wells drilled. Not one, many. In this particular image, they're showing 6 wells originating from each of these 4 pads. And notice the spacing. In one direction, about 1 mile, and the other direction, about 2 miles. That would be the uniform pattern that you would see in any area in which shale gas or shale oil is being developed. And I'll prove that to you by actual maps and photographs. 1 mile by 2 miles. So forget the notion that they're going to drill a well here, 10 miles away they'll drill another well, and everything will be hunky-dory. That's the way it used to work in New York State before shale, but that's not the way it can work in shale. So here's your shale layer. This might be the Utica. Forget about the Marcellus in here, it's too shallow, but it could be the Utica. That's this big black block. And so you see 6 wells, 3 coming down and turning using directional drilling. That's a relatively new technology that enables the wells to go in any direction for any length. You have 3 wells going in this direction, 3 wells going in that direction, and I'll prove to you in a few minutes why that has to be the case. The wells don't radiate like spokes on a wheel. They have to go in opposite directions for a very specific geological reason. But what you see here is 24 wells. And all this fuzzy stuff is meant to indicate the fracking process, which is really not fracking. Shale doesn't get fracked. Sorry to have to tell you that. Shale is already fracked. Why do you frack something that's already fractured? If the shale wasn't fractured, it can't produce. And I'll show you pictures of why that's the case. So this is an artist rendition, and as you can see, the idea here is to get as many wells as closely spaced as possible in this volume of rock. That volume of rock might contain one hell of a lot of shale gas. If it didn't, they wouldn't be bothering with it. And the idea is to get as much of that gas out as possible. And I'll show you in a few minutes where, with this state-of-the-art approach, it's called clustered multi-well pads with high-volume long laterals. All those words are depicted in this one image. Even with that, with each one of those wells taking 10 million gallons of fracking fluid, I'm going to ask you a question here because this is a serious part. What percentage of all the gas that's stored in that rock is currently being produced using this technology? What percentage would you be willing to invest your money in as a rate of return? Let's assume that there's 100% of the gas is there to begin with. What percentage of it actually comes up those 24 wells over their lifetimes?
10.
The average in the Marcellus is 5. What happens to the other 95%? Stays there. Why? Because you can't get it out.
Pressure.
Why? Because the shale is impermeable. Well, if it's impermeable, how do you get any gas out of it? You get the gas out of the fractures that are already there. That's the response I usually get when I give this talk. People's eyes light up, their chins drop and say, so it's not fracking? No, it's not. It's refracking. All you're doing is propping open the cracks that Mother Nature put there over the last 350 million years. And it's only those fractures that are storing gas that's readily available. I'll talk to you about decline curves in a few minutes, how rapidly each one of the wells sees a reduction in its productivity. After 1 year, you're only getting 50% of the gas you got on the first day. After 2 years, you're getting 30%. After 5 years, you're getting sell the well to the lowest bidder. So it's a very inefficient process. But you have to bludgeon the damn rock just to get anything out of it. That's why it costs each one of those wells $5 to $10 million. So you better hope that the amount of gas you get out of that well pays off that debt. And right now, it ain't doing it. Not at $4 a thousand. Losing proposition. All right, so what does it really look like down there? Well, I can't take you down there, but I can take you into Tagonet Gorge. How many people have walked up Tagonet Gorge? You probably walked up that stream with your grandchildren. That's a reference to the average age in the room. See, sophisticated sense of humor. You probably wondered which company came in and sawed all those straight lines in the rock, right? Which company did that? Mother Nature. How did those are natural fractures. How'd they get there?
Water.
No. 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 Gas pressure.
Oh.
They're natural hydraulic fractures.
Oh.
All those decaying bugs in the shale, all that mushy stuff that you get between your toes when you're walking in the mud along the lake here, that's decaying organic matter. And it decays into lots of things, one of which is methane. And when it decays over 330 million years at 5,000 feet underground at 200 degrees Fahrenheit, that gas creates a lot of pressure and it fractures the rock. So that's what they're drilling into down 5,000, 6,000, 8,000 feet. So here's your lateral, right? The lateral part of the well that's going along. And I mentioned that the wells always have to go in opposite directions. Are you getting the idea of why now? If all the gas they're ever going to get is gas that's stored in those natural fractures, in which direction do you want to drill your lateral? Answer, the direction that intersects the most cracks. And the geologist can tell you 5,000, 10,000 feet underground the direction of those natural fractures. Modern technology can do that. So they'll drill a well in this direction and turn around, drill a well in that direction, and they're going to intersect thousands and thousands of those cracks. Now those cracks are being squeezed by natural pressure underground. So the whole purpose of what you call fracking and what I call refracking is just to apply fluid pressure through this lateral, through perforations, holes that have been burned into that steel casing. Put that pressurized fluid into those fractures at a pressure higher than the pressure that the earth is exerting on them, and what happens to them? They open by about 1 millimeter. For as long as you can do it, you want those fractures to open up in this direction 300 or 400 feet, and in this direction for the whole thickness of the shell. So now you know why you need 10 million gallons of frac fluid. If you're intersecting thousands of these cracks, and you're opening them up each about 1 millimeter, 1/10 of an inch, and each of those cracks is going to be hundreds of feet long by maybe 100 feet wide, it takes millions of gallons of fluid to do that. And once you've opened them up, you inject proppant, crystalline sand, or ceramic beads, and the frac fluid carries the sand and the beads into those cracks so that when you release the pressure from the surface that you've used to inject that fluid, those natural fractures don't close up anymore. They're propped open. And now they're super highways for gas and oil. Got it? Here's another view. Here's any one of those fractures. They're fracture systems. Here's the shale block in between the fractures, and this shale is impermeable. For those of you who don't know what that means, impermeable means fluids don't want to flow easily through it. Name an impermeable material. Concrete? Shale is 1,000,000 times less permeable than concrete. Aluminum? Shale is about the same permeability as aluminum. All right, so the gas that's inside of this block ain't ever going to go anywhere. Not in our lifetimes, not in thousands of years. The only gas they're going to get in the first few days is the gas that's within a few fractions of an inch of these fractures. And over years, they might get the gas that can migrate over maybe an inch. And it would take centuries for the gas to migrate a foot. And it would take a millennium for a molecule of methane here to move 2 feet. That's why 95% of the gas stays in place, and the only gas they get is the one that's already out in these fractures. Got the picture? All right, let's translate it into a landscape. Upstate New York. Let's suppose that Governor Cuomo tomorrow says, let there be shale gas development. And let's suppose that somehow, by exporting enough natural gas from Pennsylvania, the price of natural gas goes up to $6 or $7 or $8 a thousand. All those companies are going to be flocking in upstate New York, and this is what they're going to do. Clustered multi-well pads. Each one of these yellow rectangles is 1 mile wide, 2 miles long. Every one of those red dots is a pad. Why wouldn't they do that? Where's the shale? Where's the shale in this picture? Everywhere. Everywhere under the picture. The shale doesn't start and stop. Okay. So you're going to drill everywhere that you can lease and that is permitted by regulation. So each one of those pads is going to have multiple wells, 5, 10, 15. The record right now is 64 wells from one pad in Colorado. The average in Pennsylvania right now is between 4 and 5 wells per pad and rising. So this idea of 24/7, 365 development, sorry to have to tell you this, it's 24/7, 365 development per well. So they drill the first well, and they might put that into production, and it might not be a year or two until they get back and do the second one. And then 3 years from now, they come back and do the third one. So how often do you have 24/7, 365? Not until they're done developing all the wells on that pad, and that might be years or decades. You don't know. They don't have to tell you. So that's what it would look like. How do I know? This is what it looks like in Tioga County, Pennsylvania. This is 2 years ago. Here's Tioga County, Pennsylvania. Here's the New York-Pennsylvania border. This is heaven. This is hell. These are the lease holdings of one company. Anybody recognize that company? No. These are the lease holdings of one company. What do you see? Tell me what you see. Do you see clustered multi-well pads? All right, so there are your rectangular-like lease holdings from one company. Every black dot is a pad. Here's a close-up. Here's Bradford County, Pennsylvania. Multiple colors. Each color corresponds to a different operator. Okay, this is April 2013. Bradford County and Susquehanna County are the most drilled counties in Pennsylvania for shale gas. They are ground zero. They are the mother lode. So they're not done yet. This is, Pennsylvania currently has, when last time I looked last week, 7,800 shale gas wells in the Marcellus drilled to date. 7,800 statewide. It's estimated by the industry that they will drill 100,000 in Pennsylvania in order to exhaust all the Marcellus gas in Pennsylvania. So how far along is Pennsylvania in its development? The answer is we're just at the beginning. It's early days. 7 or 8% of the wells have been drilled so far. So you ain't seen nothing yet. All right, there's Bradford County, and again, this map now shows every pad and all the pipelines and all the compressor stations. That's industrialization. Anybody from Bradford County? Anybody have a relative down there? This used to be thinner. Rural, agricultural, beautiful, rolling. Where's the Grand Canyon of Pennsylvania? That's what it's going to look like, and every one of these things, every one of these yellow dots at one point looked something like this. That's a typical pad during the process of fracking. So the pad has been developed. There's lots of excavation, a lot of tree removal, and these pads are not 1 acre. That's not an acre. And a lot of truck traffic to come in and drill, a lot of truck traffic to come in doing fracking. Building of artificial ponds and lakes, retention ponds first for fresh water for fracking, and then for flowback, which is not fresh water. It's the refuse that comes back up the well after fracking for temporary storage. I'm going to show you a couple more images of some pads. Here's one that has 5 well heads, so 5 wells on that pad, multiple storage units. This is a granddaddy of them all. This has 7 wells. How many acres do you think that is? Yeah, and how many trees do you think were removed? Tell me which states have regulations that require that every tree that's removed during oil and gas development has to be replanted someplace else. Would that be a good thing to require? I think so. Are trees helping us in climate change? Okay, this image shows a little bit more of the, what I call the infrastructure associated with development. Here's a pad with 7 wells. Here's the impoundment dam. Here's the nearby house. In Pennsylvania, at the time that this was done in 2009, minimum setback distance was 350 feet. Tank farms, storage tanks, it gets worse. This one shows everything. Here's a pad, here's a pad, here's a pad. Here are homes and farms. This is a processing facility. This is in southwestern Pennsylvania where the gas is wet. Wet gas means it has more than methane in it. It has higher order hydrocarbons like propane, butane, ethane, ethylene. Those come up as liquids. So you have to process, that is, separate out, refine what comes out of the well, and separate out those various components. So this is a mini refinery. Compressor stations. You're probably thinking, this can't happen around Cazenovia, but is there a compressor station around here someplace? Is there one? Have you ever heard a blowdown from a compressor station?
No, not
You want to hear a blowdown from a compressor station? You're going to hear one whether you like it or not. Okay. Let's see. You don't know what a blowdown is, so I'll have to explain it to you. A compressor station compresses. It takes gas coming out of low pressure wells and increases the pressure so the gas can go into a high pressure pipeline. Periodically, they have to blow down the compressor station, sometimes by accident, sometimes on purpose. That's 95 decibels at that fence line. That's the same as a jet engine. This goes on for hours.
What's being blown down?
Methane. That's methane. Oh, methane is never vented. Are there pipelines around here?
Yes.
Anybody know what a pig is? With reference to a pipeline, what's a pig?
Goes down the
It's an
pipe.
electromechanical device that's inserted into the pipeline in order to do internal inspection of the pipeline. But the pipeline has high pressure gas in it. How do you get a pig inside of a pipeline that has high pressure gas in it? You have a pig launcher, which is a big valve. But if there's high pressure gas in the pipeline, what happens when you open the valve? Same thing. You're going to see guys just walking around here. I hope they're not smoking. But that's methane. So even though there might not be Marcellus development around here, there's always the possibility of development from other shale resources beneath your feet. But there's always going to be this so-called ancillary infrastructure of processing units, compressor stations, pipelines, and blowdowns, and flares. Anybody been to Pennsylvania over the last couple of years in the middle of the night, northern tier of Pennsylvania? There are nights when my wife and I get in our hot tub in Ithaca, New York, on a clear night. If we look south, it's 40 miles to Pennsylvania, the sky is red. That's 200 feet of flame. 200 feet. And this would burn, typical flare might go for a day, 2 days, 3 days, 5 days, a week. So the industry clearly is very concerned about selling every single cubic foot of gas it has, right? They never vent, they never flare.
Oh.
Okay, compressor stations, this is an early design, 2 compressor units, 9,000 horsepower each. This is a super station. Each one of these has 9,000 horsepower. So you can imagine the noise level. Processing units, again, are not small. There are many refineries. So in sum, this idea that it's just fracking, it's just like everything else that's happened, nothing that I've showed you has ever happened in New York State. So how can they say to you in New York State, don't worry about it, we've been doing it for 60 years safely? It's just the same thing. That's a lie. It's not the same thing. It's clustered multi-well pads with high volume, long lateral fracking with much higher volumes of fracking fluid, much higher volumes of waste, many more truck trips, longer time for development, larger pads, more infrastructure. That's what's different. Yeah, fracking's been around for 60 years. That statement is true. Everything else about it is a myth. I'll skip this. We might come back to this during Q&A. It has to do with productivity of a well. For those of you who have leases and are hoping for millions, good luck. Yeah, first check will be the biggest one you ever see. All right. Let's go on to the second issue. As the ad says on TV, we have 4 layers of steel casing and 4 layers of cement that securely isolate our gas wells from the groundwater. We cannot possibly leak into your groundwater. If you have bad water, you always have bad water. We didn't do it. The fact is, and I'm going to show you industry data, that leaking gas wells is a chronic problem. It has existed since the beginning of gas well drilling. It's a ubiquitous problem. It happens everywhere in the face of the earth, onshore, offshore, Russia, and the US. It's a well understood problem. Everybody in the industry knows that wells leak. And the problem is unresponsive to tough regulations. Let's talk about tough regulations. They're called the 10 Commandments. Okay, let's make them tougher. Thou shalt not kill. Thou shalt not kill. It's tougher regulation. Thou shalt not kill Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday, any month of the year. That's a tough regulation. Does it stop people from killing each other? Okay. So, regulations are words. Actions are what's important. And let me show you some of the actions from the industry. Begin by some interesting peer-reviewed data. This is from a paper published by my colleagues at Duke University who went into Pennsylvania and New York and measured methane concentrations in private water wells. And then they measured the distance between that private water well and the nearest shale gas well. And then they drew a graph, a plot. Here's the distance between a water well. Each one of these points corresponds to a test on a private water well. This is the distance between that water well and the nearest shale gas well. And this is the concentration of methane in the water wells. Tell me what you see. Yeah, correlation might be a strong word, but certainly a relationship. One could conclude from this data that the closer your water well is to a gas well, the higher the probability is that you're going to have methane in your well at very high levels. And it's important for you to understand that an mg says that's milligram, thousandth of a gram per liter. Doesn't sound like much, but once you get to 10, that's the action level from the U.S. Department of Interior for hazard mitigation. It means your water well has so much methane in it that it's now become a hazard for your house. It's become an asphyxiant hazard because if you get too much methane in your house, you're breathing methane rather than oxygen. And it's a hazard because it becomes explosive. All right, so that paper was published, I think, 3 years ago, and it instigated lots of other studies. This paper suggested, since the people who wrote this paper were not oil and gas engineers, they were hydrologists, they suggested that maybe this methane is coming from leaking gas wells. No proof, just a suggestion. What does a leaking gas well, what might a leaking gas well look like? I'm going to show you a video. In the video, you're going to see that this is the well head. It's what comes out of the ground at the surface. It's called the production casing. It's a steel pipe, typically 4.5, 5 inches in diameter. It's the pipe that goes all the way down and then all the way out, 3 or 4 miles. And that's the pipe, the only pipe that's supposed to be transporting natural gas to the surface. A well that has integrity, I'm using industry parlance, industry jargon, a well that has structural integrity is a well that transports the hydrocarbon target only through the inside of the production casing. Got it? My wife saw this the first time. She said, "It looks like our hot tub." So you're wondering, why is there water here? Well, there's an excavation around the wellhead called the cellar, and it accumulates rainwater or snow melt, and it now becomes a telltale. That bubbling clearly indicates that there is gas coming up outside the well. That well has lost its structural integrity. It is transporting methane not only through the production casing, but also outside the well. It's leaking. Why would a well leak?
Bad welds.
Why would a well leak? Now, it could be that the production casing itself has a hole in it or is cracked, but it happens. But there's a much more common explanation. If you're going to drill a well, let's see how. I haven't heard anything about the average intelligence level in this area, but I'm presuming, like most upstate New Yorkers, we're all above intelligence, all above average intelligence. So you should be able to get this one. I'm going to drill a hole, and I'm going to insert steel pipe in it, called casing. And let's suppose that the casing is 10 inches in diameter. What should be the diameter of the hole that I drill? Larger. By New York State regulations, it has to be at least 2 inches larger. So which means you have a 1-inch gap between the hole that you drilled in the rock and the steel pipe you're putting in. What are you supposed to put in that space? It's called an annulus.
Grout.
A grout, a gasket. Because if you don't, then what's to stop anything that's down there from coming up outside the well? Nothing. So what does the industry universally use as a grout or a gasket? Cement. Thank you for saying that. It's not concrete. Hardened cement paste. Go to your local hardware store, buy a sack of cement. It comes in various types, so the industry has to use a certain type. Mix it with water, and you have a fluid. It's liquid cement. And you pump it down the well in such a way that hopefully you fill that gap, and then it hardens. Then what does it do? Cracks. Shrinks, cracks. What must it do? It's supposed to fill that gap continuously without any voids. It has to not shrink over time. It has to not crack over time. It has to bond well to the outside of the steel casing and to all the rock layers all the way down. And how long is that gasket? 2 or 3 miles. And how thick is it?
2 inches.
You figure out how that works. It usually works, but frequently it doesn't. So an important question is, how frequently doesn't it work? Because that tells you how frequently gas wells leak, which leads to the possibility that your gas well leakage is contaminating your water supply. And this is science that is just now being done. No one had ever gone through that whole process of a complete, total, comprehensive examination of the rate at which gas wells and oil wells leak, the rate at which they leak contaminants into the groundwater, and the probability that that leakage into groundwater contaminates your water well. Nobody has ever done that. Not the EPA, not the DOE, not the federal government, not the state governments. We're just now beginning to do that science. So here's what the industry knows. I told you it's a well-known problem. I'm going to show you that. I'm not inventing any of this. This is industry data. Gulf of Mexico. This is a bar chart. A bunch of companies went out into all the offshore platforms in the Gulf of Mexico and measured leakage, which wells were leaking, like that bubbling well I just showed you. And then they categorized the leaking wells by how old they were. So this is the percentage of wells with sustained casing pressure. Sustained casing pressure means there's gas pressure outside the production pipe. Tell me what you see. It's already written here. So you can either tell me or you can read it. Brand new wells were failing at the rate of about 5%. 1 in every 20 wells brand new is leaking. As the wells age, what happens? Leak rate goes up. I'm not going to make a nasty reference to the average age in this room again, but I'm going to point out that everybody in this room has something that's broken, or is breaking, or will break soon. As machines, we're all machines, as machines age, things fail. Okay. First time I showed this graph in public, a bunch of people from the oil and gas industry stood up and said, it doesn't mean anything, that's offshore. And I said, don't you spend a hell of a lot more money on offshore wells than you do on onshore wells? So if this is the best you can do offshore, I can only imagine what it's like on onshore. Okay, so then I got onshore data. Here's onshore data from 340,000 wells in Canada, oil and gas wells. Some were shale, most were not. Let me interpret it. This is gas migration. In Canada, as opposed to in the US, regulators go out and measure not only whether there's gas bubbling at the wellhead, they go out and measure whether there's gas percolating to the surface away from the wellhead. Because just because you don't see any bubbling at the wellhead doesn't mean the well isn't leaking. Gas could be migrating miles away and coming to the surface in some forest or some river. So they measure gas migration, they measure sustained casing vent flow. That's gas that's coming out of the annuli. And on average, 15% of those wells were leaking, but when they looked at wells that were deviated, 65% of them were leaking. What's a deviated well? Not deviant, deviated. A deviated well is one that's not vertical. By definition, all shale gas wells are deviated. Why would a deviated well leak more often than a straight well? Hard to get around the corner with that gasket, isn't it? Okay. All right, I attend workshops every 6 months. I attend webinars given by the industry. I'm a member of the Society of Petroleum Engineers. I get invited by the industry to go give talks at their workshops. They're still friendly with me. I have no problem with the oil and gas engineers. They like me, I like them. The public relations people and advertising people, not so much. They don't like me, I don't like them. So this is a webinar I attended last year. This guy said, on the worldwide currently active wells, 1.8 million currently active oil and gas wells on the surface of the earth, 35% plus or minus are leaking. More industry data. Again, this is right off of a consultant's website. Wells that develop leaks as opposed to their age. These are 1, 2, 3, 4, 5, 6 different plays around the world. I said the problem is ubiquitous. It happens everywhere. Some of these wells are in Russia. Same pattern. Young wells, older wells. We decided that we were going to do our own study because we were criticized for showing the industry data that I just showed you because everybody kept saying, but it's irrelevant. It has nothing to do with modern shale gas development. It has nothing to do with clustered multi-well pads with long laterals and high volume hydraulic fracturing. That's where the action is today, and those wells don't leak. That's a lie. So we decided to do our own study. We went to a place where there is active, modern, state-of-the-art shale gas development being performed by 60 to 70 different companies in a state that allegedly has the toughest regulations in the world. Where do you suppose that is? Pennsylvania. So we looked on the DEP website and found out that as of early this year, there were 209 cases of confirmed water well contamination from shale gas development. As of last month, that number had risen to 240. And so we said, okay, let's go look at all the data in Pennsylvania. So we decided to do our own study, and it resulted in a paper that appeared this year, earlier this year, in a very prestigious journal. That's the Proceedings of the National Academy of Sciences. It takes, you got to do a good job to get a paper published there. So we went to the Pennsylvania Department of Environmental Protection, that's their version of our DEC, and they have a publicly available database. You can go look at it tonight. You can repeat what we did in our paper if you want to. It's going to take you 2 years, but you can do it. It's all publicly available data. Nobody had bothered to analyze it. We did. So we looked at 75,000 inspection and violation records for over 41,000 gas wells. Shale gas wells and non-shale gas wells, oil wells, gas wells, all the wells, every single well that was drilled in Pennsylvania over a period of 13 years. We read all those inspection reports and all those violation reports, analyzed the data, and I'm going to show you what we found. And then we went one step further and said, well, if we have this huge database of the past, shouldn't we be able to predict the future? It's called extrapolation. If you have reliable past information, you can use modern statistical techniques and probabilistic techniques to make an estimate of what you could expect in the future. Now, being from New York State, but having been born in Pennsylvania, I was very concerned with what was happening in Pennsylvania, but I was also very concerned with what might happen in New York. So let me show you the results that were published this year. I'm going to skip all the details and get you to the end. If we did the stupid thing and just said, let's look at all of the conventional oil and gas wells, non-shale, all the ones that were drilled in Pennsylvania over a 13-year period, there were 26,000 wells, 1% of them showed by inspection reports that they were leaking. And we said, well, it's pretty low. That's amazing. Then we said, okay, let's look at the shale gas wells. At the time we did this study, there were 5,700 of them. 6.2% were leaking. Now, these wells were young, because we finished the study in December 30, wells drilled by December 31st, 2012. So the oldest well in this database was only 5 years old, and already 6% of them were leaking. So the PADEP is proud to say that only 1.9% of our wells are leaking. But they don't tell you that 6.2% of their shale gas wells are leaking. And they don't bother to tell you that and they're still young. And what do we know about the industry data about leak rate as age goes up? But it gets even more interesting, because since we're Cornell researchers and we're supposed to be brilliant, and we're supposed to ask all the good science questions, we were curious about whether there were any spatial or temporal implications in that number. First of all, we were very curious about, all wells are drilled the same way. All wells are cased the same way. They're all cemented the same way. Why would conventional wells be apparently leaking at a much lower rate than shale gas wells? Well, the first thing we found out is that these wells aren't being inspected. I told you we looked at 41,000 wells. There were 8,000 inspections. 8,000 of those wells had no inspection reports available to the public. So if you're the director of the PADEP and you're understaffed, and there's very active shale gas development going on, where are you going to send your inspectors? So if you're not looking, you don't find anything. Then we said, are there any spatial or temporal differences? And we found out that if wells were drilled before 2009 and they were unconventional, statewide, the leak rate was 1.5%. But in certain northeastern counties, it was nearly 10%. So it depends upon where you're looking, and it depends upon when you're looking. That's really curious. Why would wells in certain northeastern counties be leaking at a much higher rate than shale gas wells in western or southern counties? Really good science questions that nobody had bothered to ask before. So we have a subsequent paper under review right now where we're trying to answer that. We can talk about it during Q&A. Then we made predictions for the future. Okay, let me just go to one of these. Let's suppose that we're just worried about Bradford, Cameron, Clinton, Lycoming, Potter, Sullivan, Susquehanna. Those are the counties that we call Northeast. This graph says If you were to start today and ask the question, over this amount of weeks, what would be the proper probability that any well drilled on day one would eventually develop a leak? Got that? This is a prediction of the future. So we drill a well today in any one of those counties, and we wait 8 years. Probability is that 55% of those wells will be leaking. If they're shale gas wells. If they're non-shale gas wells, apparently only 2 or 3% will be leaking. But that's because they're inspected. All right, enough of that. Within a month after we published our paper, and by the way, our paper got the usual criticism from the oil and gas industry, that we were prejudiced, we have Park Foundation money, Ingraffia is an activist, he pals around with Yoko Ono, therefore he's a bad man. The Auditor General of the state of Pennsylvania was ordered to do an investigation of the PADEP database for quality control. That's what an auditor does. It's his job. So he audited the same database that we used to write our paper. Here's what he found. DEP uses a 25-year-old policy on the frequency of inspections, which has a loophole that only requires DEP to conduct inspections as it has the financial and human resources to do. That explains why we were missing data for 8,000 wells. When the Auditor General tested the data for accuracy, they found errors of more than 25% in the key data fields, and that as many as 76% of the inspector's comments were omitted from the online posting. Let me explain this. An inspector goes to a well with a blank inspection form. The inspector checks a lot of boxes and then writes comments like, "This well is leaking." Then that data is converted into an Excel spreadsheet with a comment column. What the inspector found is that 75% of the time, the comments weren't entered in the comment column. So what data were we working with? 25% of the data. Whatever. Okay, let's move along, because I want to save plenty of time for Q&A. Third myth, methane is a clean fossil fuel. They used to say that. But remember, the word clean here has a specific meaning. It doesn't mean dirty as in black. It means good for climate. Now we're talking about climate change. So anybody who's a denier, plug your ears. They used to say methane is a clean fossil fuel, but then they had to admit that when you burn methane, like you burn any hydrocarbon, you get carbon dioxide. There's no way around that. If you burn CH4, you get CO2, NH2O, and CO. Okay. So it can't be clean. Clean means it has no effect on climate. But anytime you add carbon dioxide to the climate, you're making it worse. So it can't be clean. So then they started saying it's cleaner. I want you to think about what I just said. Can something be safer than safe? What does safe mean? It means nothing can go wrong. So what does safer mean? Nothing can go wrong. How can something be cleaner than clean? Okay, well what they were trying to say is it's not as dirty as its siblings, oil and coal. Oh, so now the politics gets heavy. And we're seeing that play out right now in the United States. Washington is going to be a hellhole of political infighting about clean coal and XL pipeline and shale gas. That's what's happening in DC right now. So now they're saying, let's kill coal, because we got all the gas, and we can also get oil out of shale, so we can't badmouth oil too much, but let's kill coal, which would be good. Except then they have the market to themselves to charge you whatever they want for your electricity generation. Okay, so I'm going to try to prove to you with data, some of which is ours, but it's all peer-reviewed, but most of which is others, and it's also peer-reviewed, or government data, that methane can't possibly be clean or cleaner. So start with the basics. Carbon dioxide concentration in the atmosphere, you all know by now, carbon dioxide is the principal greenhouse gas that's causing human-induced global warming. Carbon dioxide concentration in the atmosphere continues to grow. Last year, reached 400 parts per million. That's twice what it was at the beginning of the Industrial Revolution. That we know. Here's what you don't know. Methane concentration, methane is natural gas, CH4, is also a greenhouse gas. And its concentration is also going up. And it's 4 times what it was at the beginning of the Industrial Revolution. And growing rapidly, especially since the beginning of the shale revolution in 2005. So what? Methane is a potent greenhouse gas, and it's emitted into the atmosphere without being burned at every possible location along the life cycle of getting gas to the market. Everything I said before. Drilling, casing, cementing, perforating, fracking, flowback, dehumidification, compression, processing, storage, transmission, and distribution. That's the life cycle. At every one of those stages, there's leakage into the atmosphere. Sometimes accidental, frequently purposeful, like the venting incidents I showed you from pipeline pigs and from compressor stations. That's purposeful, that's not an accident. But valves leak, pipelines leak, gas comes out of flowback, gas is not burned completely during flaring. So here are all the places where you get methane purposely leaked. So methane is a greenhouse gas. It's more potent than carbon dioxide. It does more harm per pound in the atmosphere than carbon dioxide. There's more carbon dioxide being emitted than methane, but now you have to ask the question, yeah, but if methane is more potent than carbon dioxide pound for pound, it might only take a few pounds of methane to do as much harm as many pounds of carbon dioxide. What's the number? According to the Intergovernmental Panel on Climate Change, as of October of 2013, if you're willing to wait 100 years to make that comparison between 1 pound of carbon dioxide and 1 pound of methane, methane is 34 times more potent as a greenhouse gas. If you're only willing to wait 20 years, it's 86 times more potent. 86 pounds of carbon dioxide does the same global warming as 1 pound of methane. Therefore, very small leak rates of methane can have very large consequences. Therefore, we have to know how much is leaking. So in 2011, 2 of my colleagues at Cornell and I published a paper that started a firestorm. There's another 4-letter word I could use in front of storm, but I won't in polite company. But it resulted in some shall we say, unprofessional and untoward reactions towards us. We had Cornell alumni writing the president of Cornell asking us to be fired. Well, you know where they were. Very bad things. Personally, hate mail. Disparaging things said about our families. Mail stolen from our mailboxes. Our computers are hacked frequently because we were bad messengers with a really bad message. So we forecast, we didn't measure anything in our paper, we didn't have the means to go out and measure how much natural gas is leaking purposely or accidentally into the atmosphere. All we could do was use the then available industry data and then available government data and bound it, an upper bound and a lower bound. And we forecast that when the measurements were made, which had never been made, 2011, nobody had ever gone out and measured it. We forecast that when the measurements were made, the leak rate would be somewhere between roughly 8% and 3.5%. Sound like small numbers, but remember, you have to multiply those by 86 or 34, depending upon your policy decision. Do you want to wait 100 years or do you want to wait 20 years? So remember those 2 numbers. This is what we staked our professional careers and reputations on. So now we have to answer 3 questions. How much methane is being emitted into the atmosphere? Not by guessing, not by estimating, but actually measuring it. And that means a large number of people have to go to a large number of places around the world and make measurements during drilling, during fracking, during flowback, during compression. You got the point, right? That had never been done. It's a massive undertaking, but it's a really important question. So I'll try to answer what we know now that we didn't know 3 years ago. That's a technology question. How much is being emitted? Go measure it. Then there's a science question. For any amount that's emitted, what's the impact on climate? Is that 34 number or 86 number the best number? Are those numbers changing? And then finally, there is the policy question. President Obama said in his State of the Union address 2 years ago, we have 100 years of shale gas supply. What if we're not around 50 years to not use it? Ooh. Okay, so how much is being emitted? Starting in 2011, after our paper appeared, people went out and started making measurements. So I'm going to report on you peer-reviewed results. Uinta Basin, Utah, 9% leakage rate. That's just upstream. That doesn't include pipelines. Denver-Julesburg Basin, Colorado, again, this is just upstream. Does not include pipelines. Anywhere between 2.3 and 7%. Remember, here are our numbers. This is leakage from the streets of Boston. There are gas lines running up and down the streets of Cazenovia, right? When were those gas lines installed? Anybody know? 50s. In the 50s? What do you suppose they're made from? Cast iron. Bell and spigot joints. Rubber gaskets. If this is what's happening in Boston, every one of these yellow bars is an indication of measured concentration of methane on the streets of Boston. In this room right now, we are breathing about 2 parts per million methane. That's the natural background level in the Earth's atmosphere. For every breath we take, every million molecules that we breathe, 2 of them are methane. That's normal. Don't worry, we're not going to asphyxiate. The room isn't going to blow up. But in downtown Boston, concentrations 15 times higher were measured. So there's leakage from pipelines. And the numbers I just showed you do not include leakage from pipelines. Los Angeles, oh, Washington, D.C. Each one of these spikes shows background levels much higher than normal, 54 parts per million. There were 5,893 pipeline leaks found over 1,500 road miles of the city, some of which were explosive. You've heard these apocryphal stories of manhole covers blowing up out of them. Somebody was smoking while they walked across the intersection. Boom. Nobody's doing anything about this. So we published another paper earlier this year. We said, well, I wonder how much methane is leaking over a gas field in Pennsylvania. So we went to the southwestern corner of Pennsylvania. Here's Pittsburgh, here's Washington, PA. This is West Virginia. And we flew an airplane over this box for a couple weeks, and the methane had equipment in it to measure methane concentration in the atmosphere. And we flew around drilling sites. I'll skip the details and get to the point, but we flew over this site, for example, and found very high levels of methane in the atmosphere, much higher than background. This is a drill site, it's not a frack site. No fracking going on here yet, they're just drilling. See this? I don't know if you can see that, it looks like smoke. It's methane. It's a flare that isn't lit. During drilling, why would they be emitting methane while they're drilling? Think about that. They're drilling down 7,000 feet to the Marcellus. What's between the surface and the Marcellus? Pockets of gas called coal seams and other shale layers. Every time they drill through one, where's the gas go? In the atmosphere. EPA does not include that in their estimates. So we found that in that area of Pennsylvania, somewhere between 4 and 12% of all the methane being produced was being leaked. Most recent papers, this is about a year ago, criticized the EPA because for the last 3 years, EPA has been lowering its estimates, not measurements. The EPA does not measure anything. The EPA asks the industry to report to the EPA what the industry says the leak rate is. Let me repeat that. The EPA asks the industry to report to the EPA what the leak rate is. Okay, and so for the last 3 years, despite the last 3 years people measuring increasing rates, the EPA has been lowering its estimate. And so this paper loudly criticized the EPA by being somewhere between 1.5 and 1.7 times too low in its estimate. The more recent paper earlier this year says we take into account all the measurements made in the last 3 years, and we think that somewhere between 3.6 and 7.1% of all the methane being produced in the United States today is not being burned. We are not co-authors on this paper. This was what we thought, and this is what they said. Even more recent, this is a paper that came out this last month, using flyovers, hundreds and hundreds of aircraft flown by NOAA, National Oceanic and Atmospheric Administration, flying all over the US and making methane concentration measurements. So this is methane concentration in parts per billion. Remember, the background level is about 2. So this is what it looked like in 2006, 2008, before there was any large shale gas or shale oil development. This is what it looked like in 2009, 2011. And notice the hot spots over the Bakken Shale in North Dakota, and the Eagle Ford Shale in Texas, and the Marcellus and Utica Shale in Ohio. So methane concentrations are increasing nationally. And this paper estimates that the leak rate is 10.1% plus or minus 7, or 9% plus or minus 6.2. There's a lot of uncertainty, but it's not 1%. Again, this is what we estimated. Here was our range. These are the measurements made by these flyovers. Their averages are well above our range. And most recently, this is satellite data. Finally getting, the US does not have a satellite in orbit that can measure methane concentration. This is a European satellite. Our satellite to do that failed on launch, and we don't have funding to put another one up yet. But interestingly, they found a really hot spot in Four Corners area, which is the epicenter for coal bed methane development. It's been going on for 20 years. And everybody in the industry knows that coal bed methane is the dirtiest form of methane emissions, confirmed by satellite. All right, so how much methane is being leaked? Somewhere around 5%. Huge leakage. So what? I mentioned before that if you're willing to wait 100 years, it's only 34 times more potent than carbon dioxide, 20 years, 86. Where do those numbers come from? Atmospheric science. Atmospheric science continues to hone those numbers and prove them. Here's the history. Back in 1996, when the Intergovernmental Panel on Climate Control issued its first report, it estimated that over 100 years, the warming potential of methane compared to carbon dioxide was a factor of 21. They updated that to 25 in 2007, and last year they updated it to 34. Over 20 years, the number has gone from 56 to 72 to 86. So we're not only emitting more methane than we ever thought, the impact of the methane that's being emitted is higher than we ever thought. Burning our proverbial candle at both ends, that's a horrible analogy to use tonight. This one's in red because back in the mid-1990s, a Republican Congress said, okay, all right, we admit there are greenhouse gases, and we admit that methane is a greenhouse gas, but let's put into the Code of Federal Regulations that ratio of methane to carbon dioxide is 21. It's now law. It's encoded in the US Code of Federal Regulations. It's 21. It's not 25. It's not 33. It's not 34. It's 21. So every time you hear the government or the EPA or Albany announce that our emissions are down, they're using that number. So you can decrease your methane emissions by 15 or 20%. That's what they claim they've done in the last 5 years. But you've increased the impact by 50%. You've lost ground. The EPA is legally not able to tell you that the best science says that that number is off by 50%. Finally, the policy question, almost to the end here. Over what period of time should we measure the impact of methane on climate change? Well, if you're an optimist, you'll say 100 years. If you're a reasonable scientist, you'll say 100 years. I don't know. I mean, things are happening now. Climate change is accelerating. We want to know what to do today. The IPCC finally said something in its last report, and they said the choice of the time horizon is a value judgment. It's politics. What do you value more? spending money in the short term ameliorating methane emissions, or spending money in the long term ameliorating carbon dioxide emissions. That's another fight that's going on in Congress right now, because certain elements in Congress want to eviscerate the EPA. Last two slides, the most important ones I'm going to show you. I always save the most important to the last. This is the best available climate science condensed into one picture. This is year. Here we are in 2014. This is global warming measured in degrees centigrade. These are measurements of global warming. So over the last 100 years or so, we've warmed about 7/10 of a degree centigrade. You've heard that. So this is actual measurement. These are computer simulated predictions. Not one, but the result of many different research groups around the world running multiple simulations using Monte Carlo simulation techniques, if that means anything to anybody, for 4 different scenarios. Each one of these colors corresponds to a different set of expectations of what will happen in the future. This is the reference case, also called all the above. Business as usual. Keep doing what we have been doing, do more of it. Produce as much coal, oil, and natural gas as you can and burn it. Computer simulations say we get to 2 degrees centigrade in 2042. Plus or minus, because these are computer simulations and not exact. So here's the error bar. It could be that we don't get there until 2070, but it could also be that we get there in 2035. 2 degrees centigrade is what the climate scientists say is the point of no return. If we get to 2 degrees centigrade, bad things happen that are irreversible. Melting Arctic ice, melting Greenland ice cap, rising sea levels, increasing salinity in the oceans, all the more violent snowstorms. Okay, so if instead in 2010 we had started to take global measures to decrease carbon dioxide emissions, but forgot about methane, just say, let's just work on carbon dioxide, then the computer models say, not much difference. You know, maybe you don't get to 2 degrees centigrade to 2045. That's because carbon dioxide doesn't have much quick effect on climate change. It's not as potent as methane. If in 2010 we had decided to decrease methane emissions globally and also decrease black carbon emissions, that's soot, the stuff that you see coming out of diesel stacks, and what you get when you burn biofuels, smoke from fires, the climate is very responsive. You don't get to 2 degrees centigrade until 2060. The correct thing to do, of course, is all of the above. We should have been starting way back here, or at least in 2010, to globally decrease the use and the emission of all fossil fuels, which would be reducing carbon dioxide, methane, and black carbon. And the computer models say that our kids and grandkids have a good chance of never getting to 2 degrees. But we didn't do anything in 2010. And we're not doing anything in 2014. So this experiment is ongoing. Every year they rerun these, and so they don't have to extrapolate as far, so they become more accurate. So that's the science, and I'm going to conclude with one last slide, which is the politics. So this is what the scientists say. Notice in 2040, we're going to be here, or someplace in between, depending upon political will, how you vote, how you pay taxes. I'm talking about you collectively, 322 million Americans. Now I'm going to show you the political forecast. This comes from the United States Department of Energy. They have an annual energy forecast. So this is year, and this is a breakdown of energy consumption by fuel in the United States. How do we drive our cars, heat our homes, heat our water, make electricity, industrial processes, feedstocks. That's where all the energy goes. So this is history. This is actual data from here to the left. So in 2011, this is the latest year they've done this analysis, These are the percentages of each of these kinds of energy that we were consuming in the U.S., that you were consuming in the U.S., using the collective you. And our Department of Energy, which of course is a department of the current administration, so you assume that they're forecasting based on current policy, predicts in 2040, this is where we'll be. What do you see?
Nothing.
Business as usual. Do you really think that by 2040 we will have increased renewable energy in the United States by 3%? I mean, we've probably done that since 2011. But that's the stuff that Congress is talking about, and that's the stuff that Congress is going to be fighting back against the president, who's fighting with the Congress to fight back against him. I don't understand this. This is what the president sees as the future. It's totally contradictory to everything he announced this week about the deal with China. I don't understand. Somebody explain it to me during Q&A. Okay, so that's it. I covered the 3 points. There are a lot of things we didn't cover. Hopefully we can do more during Q&A. Thank you for attending and participating. It's really an honor to be with you. I'm sorry I talked so long.
So here's the deal. We have to be out of here by 9. We have to be all cleared out, stack all our chairs, not the soft chairs, but all the chairs have to be put back. So we've got probably about maybe 10 minutes for some key questions, and then we need to begin to throw out. While we're having the Q&A, we're going to pass around. I want to pass around the basket and ask people to donate some money into, which is going to go to Tony's organization for engineers and scientists. There it is. Physicians, scientists, and engineers for healthy energy. So any money will support his work in that way. He's doing this for free. He's taking his time and came here on his own dollar, and so we totally appreciate him for volunteering to be with us. So another round of applause for just being here. We're also going to circulate a checklist, a quick vote. What's your vote on yes or no on the issue of drilling in this area here? Where do you stand on that? And then there's also, we'll pass around, if you want to be on a mailing list, an email list, we have a mailing list. It's blind copied, so nobody will get your email. And I send out things that are just, I don't send out a lot of stuff to people because there's so much stuff that comes through me. So on this list, I just get things that I feel are relevant to what's going on around us, so I don't bombard you. So if you want to be on that list, give us your email list, and if you just want to be in contact in case we do other things. So, back to the questions. We'll start over here and kind of sweep to the left. Yes, sir.
Professor, what do you suggest we do personally? Should we be moving away from natural gas?
The answer is yes. Everybody should do whatever they can in their personal lives to decrease their demand for fossil fuels and increase their demand for renewables. That's how this country works. We're a capitalist society. We respond to where the money goes. So how do you decrease your demand for fossil fuels? You can do that in your home. You can do that in your car. You can do that in your business. You can do that in your university. Because nobody's going to divest, right? How do you increase your demand for renewables? You can do that in your home, buy solar panels, do air source heating and cooling, do geothermal heating and cooling. You can do that in your communities by getting involved in community-scale solar farms, community-scale wind farms. Go online and ask that question. How can I reduce my consumption of fossil fuels? Demand that the electricity currently coming into your house be coming from a renewable source. You can do that in New York. You do know that for every watt of photovoltaic power that you purchase today in New York and install for your home, New York State pays you 90 cents. They write you a check for 90 cents. Plus you get a New York State tax rebate and a federal tax rebate. Same thing for solar hot water. It's never been cheaper. And if you don't want to buy it, you can lease it. So, good question.
What's your opinion on, or feeling about the odds of Cuomo going ahead with or without the full health study?
Okay, so I'm not a politician, so my opinion is worth the same as anybody else's in the room at this point. I don't have an inroad into the governor's mansion. What I do know is that during his debate with Astorino, he said that he would decide on the basis of the ongoing health study what to do by the end of this year. He said that. And everybody thought, well, heat of the debate. But then during the press conference after he won, he was asked, did you mean that? And he said, absolutely. I will have a decision by the end of the year. Now, you can interpret that as a politician speaking, right? What decision? He's going to decide to read the health report or not read it. He's going to decide to make it part of a next generation SGEIS. He's going to ask DEC to reformulate its proposed regulations based on it. Who knows? But my personal opinion, he will do one of two things in the next 6 months. He will decide based on this health study that more study is needed and New York State will remain in a moratorium as long as he's governor. He can do that. Or he can say, okay, let's let one or two companies come to one part of Broome County and show us their stuff, which would be nonsense. It's statistical nonsense. It has no bearing whatsoever on any of the harms I showed you because it doesn't include cumulative impact. It doesn't sample enough of the statistics. They can drill 10 wells and all 10 of them will be fine. It doesn't prove that the 11th one wouldn't leak. But from a technical point of view, it means nothing. From a political point of view, maybe he sees a calculus. Yeah.
The figure you used with refracking, I believe, was like 5% that they get out of it.
Mm-hmm.
And so my question is, if we look at offshore oil, and they're businessmen, so what are they looking at to make that, if it's that low of a figure, to make a profit? Are they able to freeze gas and not freeze oil, which would make the transportation costs lower, and they make the profit in that regard? Or what is it that makes that desirable?
We could spend an entire evening talking about the economics of oil and gas development, conventional, unconventional, onshore, offshore. It's extremely complex, as you can imagine. It's capital motion all the way across. So right now, developing shale gas is a losing proposition except for a few companies who have very low overhead, and happen to have leased in the most productive areas. Cabot Oil and Gas in Pennsylvania, for example. They happen to have gotten Susquehanna and Bradford, hotspots. They make money.
By sheer volume then?
By sheer volume. Okay. The other companies are losing their shirts on shale gas. And they will until the price of shale gas goes up. Now, how do you get the price of shale gas to go up? Export it and reduce the supply to the U.S. and make it an internationally traded commodity like oil. The very first talk like this that I gave in a church in somewhere near Vestal, 2008, somebody asked that question. I said, the plan all along has been and will be to export U.S. natural gas.
And that can be frozen and easily transported.
And it can be frozen and easily transported.
Okay.
Well, it can be frozen at great energy expense and cost, and it can be transported at great energy cost and expense, and it leaks from. So from an environmental point of view, it's the worst thing to do. From an economic point of view, it's exactly what they want to have happen. And so what that will do is decrease the supply of natural gas that's available to the U.S., but it will make it profitable for those who are still developing it for the next 5 or 10 years, which is as far out as they're worried about. Where should I go next? Yeah.
We have a local dilemma. There's an infrastructure build-up going on. I'm sure you're aware of the Dominion Market project. One of the very large new compressor stations will be within 2 miles of the town of horsepower to begin with. What can we do? There is a meeting tomorrow night in Morrisville. It's very heartbreaking.
What can you do? There's a range of things that people can do. One is to sit back and watch.
No.
The other is to attend the meetings and bring information with you and present the information in public fora,
Yes.
where you've been legally entitled to do that, and hope that that information has an impact on whoever's making the decisions.
It's FERC.
That's the way it's supposed to work in our country, that the people speak.
It's FERC.
Yeah, I know. So you know what's happening in Washington with FERC right now?
Yes.
FERC is being called out finally as the villain, the rubber stamper. That's what they've been. Everybody in the industry knows it, everybody in government knows it. Finally, the people are beginning to figure it out. So bring political pressure on them. The next extreme is what's happening at Seneca Lake right now. You can, everybody has to decide on their own in this society. You can never be violent. That's never permitted. But you can be anywhere from I don't give a damn to I'm going to chain myself to a fence and go to jail and not let them do it. Or at least make it look like they can't do it. And then that helps you sleep better at night, but it's going to look bad on your record. I mean, their 90-year-old woman got arrested and handcuffed.
I saw that.
Okay, she has principles. Sandra Steingraver I think she's going to be in jail 3 times in 1 year.
Yep, he's meditating.
You want, I know how frustrating it is. Think how frustrating it is for the scientists and engineers who go through all this effort of doing all the research, going through all the effort of going through the routine, not the routine, the rules of getting a paper out in a really good journal. And then you don't get any response. Nobody in the government listens.
I'd like to just note out, though, that I've just noticed that there are several elected officials from our town boards here in the room tonight, so they are listening.
Good.
And I want to just say thank you to them for coming.
Thank you. Yes, thank you.
Maybe one more question, then we should wrap it up.
Tony, I've got a question. Tony, welcome to Cazenovia.
Great to be here.
This is the home of Chittenango Falls, Perryville Falls, Stockbridge Falls.
Yeah.
It's the end of the
Is it good fishing up here?
Yeah.
I'll be back in the spring.
It's the end.
Anybody fly fish?
It's a trout stream.
Somebody
end.
take me fly fishing up here in the spring.
It's the end of the Appalachian Plateau. The shale sticks out of our gravel beds up in Fenner. We like shale in our driveways. All the way to Clockville, we've got shale beds. My farm is in Clockville. Go get your shale. The thing is, that's the top shale. Boy, if you look at it, you can see oil right in a piece of shale right there. The Utica shale sticks out when we go to Little Falls. You guys can run around there. That's the end because the Oneida Lake is the river, Lake Ontario, and then you've got the oldest mountain range in the world in the United States, the Adirondacks. So what we see is the top part of the shale. Fellas and girls, I don't think in my children's lifetime you're ever going to see a drill rig. I'm sorry. You're never going to see a drill rig in Fenner, town of Fenner, where they can see over the cliff and down to Oneida Lake. The shale is too thin and the gas is gone when it was fractured. We're fracturing it with our little mines that we have out there. Peter might have one. Thanks. Thanks all.
Okay, if you have more money, put the money on your way out in the basket.
I don't want to see it.
I don't want to turn down your money. They're waving money at me.
Thank you all very much. Great audience.
And to the people